So the next thing I want to talk about is the Arrhenius equation. So, we talked about temperature, we talked about concentration, we talked about activation energy. So how do we all relate this into one equation? Now, Arrhenius, this guy, discovered the most reaction rate data obeyed an equation based on three factors: the number of collisions per unit time, the fraction of collisions that occur with the correct orientation, and the fraction of the colliding molecules that have an energy equal or greater than activation energy. So three things: number of collisions, right orientation, and enough energy. Okay, and he came up with this equation: K equals AE to the EART. Come up with this. That's the Arrhenius equation. It's very important. Write it down. Okay. All right. So, sorry I'm going so fast, but it's just to save time. So K is the rate constant, EA is the activation energy, R is the gas constant, 8.314. Very important. It's not 0.0821. It's 8.314. Okay. And then T is the temperature in Kelvin. Kelvin. Got it? A is called the frequency factor. It is related to the frequency of collisions and the probability that a collision will have a favorable orientation. Both A and activation energy, both the frequency factor and the activation energy, are specific to a given reaction. That means they will never expect you to know this. They will never expect you to know what A is, what EA is. What you do have to understand is you do have to know how they relate to each other. So, like, for example, if they ask you what happens with an increase or a decrease in temperature, well, if you decrease in temperature, then obviously you're going to have a much smaller rate constant. If you increase in temperature, you're going to have a much larger rate constant. And you can see this with how this equation is set up. So let's talk about determining the activation energy. So sometimes EA may be determined experimentally, but sometimes we can actually kind of look at this, and we need to take the natural log of both sides, in other words. So if we took the natural log of this, ln k equals ln a e to, negative whatever. Basically, what you're going to get is you're going to get something like this. And what I recommend is literally just to memorize these equations. It's not that bad. It really isn't. And then basically you're going to have K1 over K2 equals EA or K2 minus T1. Alright. So don't worry about the second one right now, but just take a look at the first one that I've written for you. Okay. The second one relates to a graph of ln k versus 1 over t. It's going to have a slope of negative activation energy over r and a y-intercept of ln a. So this is kind of what I showed you on the second one is kind of like the alternate to that, in which you can kind of compare two temperatures. So that's kind of like if they say, oh, if I have temperature 2, if I have temperature 1, what happens to my rate constant, or what happens to the ratio of my rate constant and all that stuff. So these three equations that I've shown you right here, you might want to pause the video just so you can really take a look at them. Those three you really do have to understand, and it's not so much that you have to know how to do these calculations, but it's more so that you have to understand how they relate with each other conceptually. Okay? And I explained all that in my previous video, so hopefully you understand. Don't want to go into the whole derivation of how these things come to be, because then it wouldn't really help you on the test. No matter what, you can derive these equations no matter what, but the problem is, do you understand them and can you apply them? Alright, So let's talk about reaction mechanisms. Reaction mechanisms are a kind of tricky kind of things because you really have to take a look at what the rate determining step is, what's the slow step, what's the fast step, what do we have to do in case where our intermediates cancel, stuff like that. So the balanced chemical equation provides information about substances present at the beginning and at the end of the reaction. A reaction mechanism is the process by which this reaction occurs. Mechanisms provide a picture of which bonds are broken and formed during the course of a reaction. And then we have these things called elementary reactions. There are any processes that occur in a single step. The number of molecules present in an elementary step is the molecularity of that elementary step. Unimolecular reactions involve one molecule, bimolecular two, termolecular three or more. Okay? So what happens with multi-step mechanisms? And I find that a lot of people have this confusion as to what exactly this means. Well, the most important part is that we have to understand that unimolecular processes are first order, bimolecular processes are second order, and termolecular processes are third order. Now, let's talk about the rate determining step for a multi-step mechanism. All right. Most reactions occur by mechanisms with more than one elementary step, but often one step is much slower than the others, and that is the step. That's the hump. That's the activation energy hump. All right. Once that goes, everything else goes very fast. This is called the rate determining step. It determines the rate. Okay. It's always going to be the slow step. Slow step, that's going to be the rate determining step. Okay. So if we have a reaction, right, NO2 plus CO yielding NO plus CO2, and I said step 1 was the slow step, step 2 was the fast step. I'll write all this out for you, okay? So don't stress out. NO2 plus CO yielding NO plus CO2. Step 1 is going to be NO2 plus NO2, K1, NO3 plus NO. That's the slow step. Step 2, NO3 plus CO, K2, NO2 plus CO2. That's going to be the fast step. Okay, now check this out. Again, remember, you can pause this video at any time in case I'm going too fast. So, if K2 is much bigger than K1, then the overall reaction rate will depend on the first step, the rate determining step. In this case, the rate is equal to K1 NO2 squared. Okay? Now, this is very important for you to also realize is that this theoretical rate law is in agreement with the experimental rate law. This supports and does not prove our mechanism, which means yes, we do need to do it experimentally, but if we were just going to derive this theoretically, then theoretically is K1 NO2 squared. Okay, so what happens if this gets a little bit tricky? What happens if the mechanism is with a fast initial step? So it starts with a fast step, and then it turns into a slow step. So don't freak out. Let me just get another piece of paper here. So let's consider the reaction 2NO plus Br2 yielding 2NOBr. Okay? And step 1 is NO gas plus Br2 gas K1 K negative NOBr2. So this is a little bit tricky, so make sure you pay attention. Again, pause the video and take a look at these reactions and copy them down before you listen to me. I do go very fast. So. Okay, make sure you get that down. It says K1 on top, K negative 1 on the bottom, K2 on the bottom. Top is fast, bottom is slow. Okay? Alright, here we go. Alright, so there's a problem to this. This rate law depends on the concentration of intermediate species. What does this mean? Intermediates are usually unstable and have low or unknown concentrations. We need to find a way to remove this term from our rate law. So we can express the concentration of NO-Br2 in terms of NO and Br2 by assuming that there is an equilibrium in step 1. In other words, therefore, we can say K1 NO-Br2 is equal to K negative 1 NO-Br2. If we solve for NO-Br2, it's going to be K1 over K negative 1 of NO and Br2. Okay, if we rearranged everything, our overall rate law would be rate is equal to K2 1 over K negative 1 NO Br2 NO, which is pretty much the same as our initial rate law, which is K2 NO Br2 and NO. But because NO Br2 is the intermediate, that's why we had to substitute for it. So there you go.